All right, so we're going to look at L'Hopital's rule. So this is not L'Hospital's rule, it's L'Hopital's. And this is a pretty easy to understand, easy to use rule. And it's a minor topic that will help you out a lot later. So it says here, suppose that you have one of the following cases. And then it gives you a limit, f of x over g of x as x goes to a. And we get an indeterminate form of 0 over 0, or the indeterminate form infinity, any combination of plus or minus infinity over plus or minus infinity. So if you get one of those cases, if you get an indeterminate form, and there are actually more indeterminate forms, but these are the ones that are the most common, the ones that we'll work with today. If you get one of those, then you can use L'Hopital's rule to find that limit. And all L'Hopital's rule says is that once you determine it's an indeterminate form, then if you derive the numerator and the denominator and try again by, evaluating the limit, then it might, give you your solution right there. Sometimes there's multiple applications that you'll have to do this, so you'll have to use L'Hopital's rule 2 or 3 times. So I will do this first problem here. So the limit is x goes to 4 of x squared minus 16 over x minus 4. So one way we could do this is to simply, factor x squared minus 16, cancel out the x minus 4, and then plug it in. So this is one where L'Hopital's rule can be used, but it doesn't need to be. We're just using it because that's a good starter example. So if I evaluate this directly by plugging in 4, I will get 0 over 0. You have to show this step. And the reason is that if you plug in your value and you get, a specific number out of it, then you don't need to use L'Hopital's rule. So don't use it when you don't need it. Use it when you get an indeterminate form. So make sure to show that it is an indeterminate form. Okay, so with this, I am just going to rewrite it. The limit is x goes to 4 of this function, and I'm going to derive every term in the numerator and denominator. So in the numerator, I would get 2x, and in the denominator, I would just be left with 1. So if I plug in a 4, this limit is equal to 8. And that's it. So that would be a very simple application of L'Hopital's rule. Okay, here's another example, and let's look at this. So the question is, do you always need to use L'Hopital's rule from the start? And so here's a good example of a problem where you wouldn't. So this one, 4x squared minus 5x divided by 1 minus 3x squared. If we're evaluating the limit at infinity, we're really just focusing on these leading terms. So this would be 4 times infinity squared divided by 3 times infinity squared. So this limit value would actually just be 4/3. So the only reason I'm putting this one in here is to show that you want to try to evaluate the limit immediately if you can, and if not, then use L'Hopital's rule. So this is one where you would not need it. But let's go to a couple other examples where it's a little different. So this limit value, early on in the first few months of this class, we covered this limit. The limit is x goes to 0 of sine x over x. So this one, I know the limit value is 1 just from memory, but here's a way to just get the answer using L'Hopital's rule. So if I evaluate this, sine of 0, the limit is x goes to 0, and I plug in the x equals 0. Sine of 0 is 0. And if I put a 0 in for x in the denominator, I get 0 over 0. Therefore, it's a candidate for L'Hopital's rule. So what I'll do is take the derivative of the numerator and denominator. And this is a fairly quick problem. The derivative of sine is cosine. The derivative of x is just 1. And then you try to plug this in again. So cosine of 0 is 1. So this limit is equal to 1 over 1. So it's just equal to 1. So that limit, even though we were memorizing it before, you can see that finding the solution to it is actually pretty simple with L'Hopital's. Okay, so this is another one. So some of these are, this is a weirder looking limit, and that's when this is most useful. Polynomials and that sort of thing, you're going to try to factor and cancel usually before. So we plug in infinity, not plug it in, but think about it. It would be e to the infinity, which would be a big infinity. And in the denominator, we have infinity squared. So we have this indeterminate form of infinity over infinity, and therefore use L'Hopital's rule. So again, really simple in these cases. The derivative of e to the x is e to the x. The derivative of 2 or x squared is 2x. And we could think about evaluating that already. It hopefully is going to make sense. This limit is going to evaluate to be infinity, but it doesn't, let's just make it obvious. So I'm going to try that again. So let's use L'Hopital's rule again, because I want to make this super obvious what the answer is. So we do know that e to the x is going to grow a lot faster than 2x, so it has to be infinity. But if we derive that one more time, we'll get e to the x over 2. And now we can see if we plugged in infinity, it's going to be e to the infinity divided by 2. And so this limit value would be infinity. So that would be 2 applications of L'Hopital's rule for one problem. And let's do another one. Okay. The limit as x goes to 0 of this, so we check to make sure it's a candidate by evaluating at 0, and we'd get a 0, and then cosine of 0 is 1. So this would be 1 minus 1, or 0. So yes, we can use L'Hopital's in this case. And let's derive it. Always get in the habit of copying the limit part, because I know it's easy to get lazy there. And so numerator is 2x. In the denominator, the derivative of cosine is the negative sign, and then we have that negative in front of it, so this would be positive sign. And if we evaluate this, let's do that. So 2 times 0 would be 0. And then as long as sine of 0 is not 0, if it's a number, then we have a limit value. So this one, sine of 0 is 0. So we don't have the limit value. So then we have to go through this one more time. So it would be, let's actually back up on that. Just do it right there. So this would be the limit. As x goes to 0, we're going to use L'Hopital's again. And in the denominator, we get cosine of x. So as long as cosine of x is a value that's not 0, we're good. So cosine of 0 is 1. So this is just 2 over 1, or 2. So using L'Hopital's rule, you want to first, show the indeterminate form. Take the derivatives, good, and then I tried again. I plugged in that 0, because if it works right there, great. And if it doesn't work, I then take the derivative again. And you can use this, as many times as you need to make it possible to evaluate the limit at the value given. Okay, so we have this last example here. Now there are countless examples online if you wanted to pull up more L'Hopital's rule examples. Usually students don't need them. After 4 or 5 examples, it's a fairly simple topic. Okay, so with this one, let's do our evaluation first. So I'm going to plug in infinity. So in the numerator, if I plug in the natural log of 3 times infinity, I would get infinity. And in the denominator, if I square infinity, I'll get infinity squared, so that would be infinity. So it's a candidate for L'Hopital's rule, so let's just go through it. So this is the same thing as the limit as t goes to infinity. And then to derive natural log of 3t, take the derivative of the outer function, which is 1 over 3t, and then we multiply by the derivative of the interior function, which would be 3, and then I divide that all by t, 2t. All right, now I can cancel these 3's. I'm going to rewrite this so it looks easier to look at. So then I have 1 over t times 1 over 2t. So all I'm doing is avoiding the division of flipping fractions just by factoring that numerator out. So this is now 1. The limit as t goes to infinity of 1 over 2t squared. And if we plug in infinity, the denominator is going to grow endlessly. So you'd have 1 over infinity, which is going to tend to 0.